Today we're going to be talking about the difference between relations and functions. And the best way to do that just might actually be looking at a picture of a relation and a function and see how they differ. Right here is a key concept of four ways to represent relations. And I think we may have seen this inside the classroom the other day, where in essence this was basically numbers. This was the graph, obviously, table of values, and also we didn't see anything about a mapping diagram. That's going to be a little bit different today, but you get the idea that you had numbers, algebraic expressions, also the graph, and some kind of sentences which describes the relation or the function. So let's take a look at some of these ideas they have here. Again, these are ordered pairs, input and output. A table of values right here, your x, y, you're used to those T-charts, and obviously your graph. But this mapping diagram might be a little bit different. And all it is just a list or an array of all your inputs, your x values, and match them up with all your outputs, or your y values. -3, 4, 3 goes to -1, 4 goes to -1, and 4 goes to 3. 4 to -1, 4 goes to 3, similar to our ordered pairs. So let's take a look at representing a relation. This guy has obviously doing a little skydiving here, and this here is going to be a pictorial representation of that skydive. And over to the left you have the table of values. If you want to look at this as a T-chart, that might be a good way of doing it. In other words, your time is your input and your height is your output. Ordered pairs again, and then let's get back to the mapping diagram. You plug in 0, spits out 10,000, plug in 4, plug in 8, plug in 12, and so on. You'll see the mapping diagram. Now, two other, I should say probably the first two vocabulary words for this section are going to be domain and range. These would be great notes to put down in your Cornell notes. Domain is related to all the inputs, in other words, the x values, and the range is related to all the outputs and the y coordinates, the y values. Finding the domain and range, what you might think is might be a difficult idea, is actually very simple. Remember, the domain is associated with x, and the y is associated with the range. So if you look at all the red numbers here, all those numbers in line, this would represent your domain. Same thing for all the blues, that would represent your range. So this would be a relatively easy question to solve. What are the domain and range of this relations? Well, your domain would obviously be all your x values, and your range would be all your y values. So let's take a look at a special kind of relation. It's called a function. A function is a relation in which each element in the domain corresponds with exactly one element of the range. In other words, there is a one to only one relationship. Here we go. One and only one. One and only one. One and only one. This here is a function. There are no values in the x that goes to two different values in the range. It goes to one and only one. Let's take a look at a couple other setups to determine whether or not there is a relation or specifically a function. Now the domain and range, remember, those are associated with your x and y values. We have 2 going to -3, 2 going to 3, 3 going to -1, 4 going to 3, 6 going to 6. Since you've got this little v right here, you can tell right away that it is just a relation. Because this is not a one and only one relationship. One here and another one to the 3, that is just a relation. Let's take a look at this setup and see if we can determine whether or not it is a relation or a function. Let's look at all the x values and see if there is anything the same in the domain. Is there anything the same in the domain? -7, 9, 14, 7. No, therefore this is a function. Now, something you might be asking yourselves, well, what's the difference between a relation and a function then? Think of this whole big blob as relations. And then this subpart of relations, your functions. You can be a relation without being a function, but you can't be a function without being a relation. Hopefully this little idea here will make sense the more we get to use these. All functions are relations, but not all relations are functions. Hopefully that'll help. We'll see. Let's take a look at determining whether or not something is a function by looking at its picture, in other words, its graph. One thing we might remember from Algebra 1 is called the vertical line test, or maybe even from geometry. And all it says is that if you've got a graph and you can draw a vertical line and it goes through once and twice through the blue graph, then it is just a relation and not a function. Here, let's take a look at a vertical line. Let's use, this one right here. Pretty vertical line. And we can go ahead and move this around the curved graph here and see that it crosses once and only once. This picture, however, it crosses twice, and with this picture, once and only once. You can also check these for do your vertical line test on your own and put those in your Cornell notes. Let's take a look at the function rule and the function notation. The function rule is actually an equation. So this function rule is your equation. The function notation, the big thing here is notation, and that the word note is in there. It may look like not, but it's really note if you think about it. The function notation means that you've got an equation that you represent as a function. This part right here tells you right away it is a function. And it's a function f of x. That's how that's described, f of x. It is just a notation. This does not mean f times x. I'll repeat that. It does not mean f times x. It just represents there is a function, and when you plug in x, this is what it's going to look like. Just like right here. This is a function. When you plug in 1, this is what it's going to look like. A couple other vocabulary words similar to those are going to be independent variable and the dependent variable. The independent variable is going to be associated with x. The dependent variable is going to be associated with f of x. You will notice that y and f of x are really the same. They're the same thing. This could be considered y, this could be considered f of x, as long as we know that this is a function. Let's take a look at using function notation. F of x equals negative 2x plus 5. What is the output for these inputs of negative 3, 0, and 1/4? Negative 3, 0, and 1/4. Here is your function rule. In other words, the equation. And then again, here are your outputs. So if I was given f of x equals negative 4x plus 1, and I plugged in negative 2, here's what it would look like. Take the function, plug in negative 2, and here's what it looks like. Negative 4, oh, I can do better than that. Sorry about that. How about negative 4 times x plus 1? In other words, when you plug in negative 2 into your function, it's going to simplify to positive 8 plus 1, otherwise known as 9. I suggest going ahead and doing these other two in your Cornell notes. Now let's talk about converting English into Mathanese. The ticket price to a concert are available online for $35 each, plus a handling fee of $2.50. The total cost is a function of a number of tickets bought. What function rule models the cost of the concert tickets? Evaluate the function for 4 tickets. Well, it sounds like a lot, but it's really not that bad because your cost is going to equal $35 times each ticket plus the $2.50 handling fee. This is your function rule right here, and you're supposed to evaluate it for 4 tickets, so your total cost is going to equal $35 times 4 tickets plus $2.50 for shipping and handling. Your total cost is going to equal 140 plus 250, which is going to equal 142.50. I think nowadays that's kind of a cheap concert. Let's take a look at determining whether each relation is a function here, here, and then list the domain and range here and here. This would be good practice in your Cornell notes.